So good evening, everyone. Welcome to our formal or informal Cape Centre monthly meeting. I'd like to take the opportunity to say hi and welcome to each and every one of you. We're currently 34 participants in the meeting, and it's nice to virtually see all of you and have a good chat with you. I'd like to take the opportunity to also welcome some of our new members. So we've got Danny Dinnebrega, that's a new Cape Centre member, and that's just joined us yesterday. So Danny, welcome to Cape Centre, and as I said to you on my chat, you've come to the right place. Hope you've got lots of money to buy telescopes, because with certain people in the audience, I'm not going to mention names, you tend to spend all your money somewhere. And you're definitely in the right crowd. Then I'd also like to welcome, I don't know if the person is in, no, it's not in our chat yet. So I'll give him a welcome later as soon as I actually see him in. All right, guys, so tonight we've got the privilege of having David Buckley with us. So David was the SALT project scientist during the design and construction phase between 1998 and 2005. And he was then appointed as the first SALT astronomy operations manager, and also the SALT science director from 2005 to 2015. David, it is a great honor and privilege for us to have you in our meeting and to be able to listen to one of your presentations tonight. As I said to you earlier,
Thank you, Marius. It's a pleasure to be here.
Thank you so much. What I'm going to do, David, is I'm going to hand over controls to you, and I'm going to make you co-host now. There you go. You can just confirm if you can see it.
Yep.
All right, then the show is yours, and please tell us a little bit more about yourself as well.
Sure.
Okay.
There's
so many mics that are open.
Yeah, I will be asking everyone to just please make sure that you're muting your microphone. Otherwise, I will be going through everyone and just muting it. David, over to you.
Thanks very much. Thanks very much, Marius. So it's nice to be talking to the Cape Centre again. I was trying to remember the last time that I actually had given a talk. It's a couple of years ago, and so it's really nice to be able to talk to you today about the work that I've been involved in transient astronomy. And the title, as you know, is Things That Go Bump in the Night, which is exactly what transients are. They're things that suddenly appear in the universe where maybe before there was nothing, or there was nothing unusual. So my foray into this started actually in 2015, when my sort of managerial and administrative roles in running SALT science operations came to an end. And that was a sort of unusual period, because I'd dedicated over 10 years of my career to seeing SALT built. During that period of time, my research took a bit of a back seat, as you can imagine, because there basically wasn't time to do that. It had to be fitted in between other things. So in 2015, it was a situation where I guess the sacrifices that I had made in that period to see SALT become a reality was something where I was beginning to reap the benefits of it. And so that's when it all started. The work that I'm going to be talking to you today about is, or tonight about, is just a summary and maybe some highlights of some of the work which I have been leading with the so-called large science program on transients on SALT. And this is a program which involves many astronomers, many students, postdocs within South Africa and internationally amongst our SALT partners, as you'll hear. So let's just get on with some definitions of what I mean by transients. So we know that the universe is not constant, although we might be sort of led to believe that it is, because you go outside every night and you see the unchanging constellations, generally speaking. And we do see variability, time variability in like variable stars and so on. And we see transient events, things like meteors, comets, transient events. But so are nova and supernova and other things in the universe. And so transients in general are things that can be from the very closest, like, for example, near-Earth objects, which come close to the Earth or maybe even into the Earth's atmosphere, to the most distant and most energetic objects in the universe. And so it covers the whole gambit of astronomical objects. And with the advent of new facilities, new observatories, and both ground-based and space-based, a whole new sort of activity has developed over the last decade or so of looking at the time variable and transient universe. And so the two objects which are shown in this slide on the left is perhaps one of the most fascinating, most important events to have happened recently in astronomy. It's the artist's impression of two neutron stars which merged in 2017 and caused a huge pulse of energy that was detected in gravitational waves. And it was the first time that we were able to actually find a optical counterpart or an electromagnetic counterpart, because it was not just in optical, it was also in gamma rays and eventually in radio wavelengths as well. But the first time of the association of an electromagnetic counterpart to a gravitational wave source. This whole area of gravitational wave astronomy observationally really only started in 2015 with the first detection of gravitational waves from merging black holes.
Sorry, David.
Sorry, was that a question?
No, that was just me. Are you sharing a graphic with us at the moment?
Oh, sorry, I thought I was, but so you're seeing
Sorry for
nothing.
the interruption. Yeah, we're watching your wonderful video feed. I'm just making sure that you are
But you're only
sharing
seeing me. But you're only seeing me. Okay, sorry. Let me make sure I thought I'd put the screen share on, but let me make sure that I have. And there we go.
There we go. It's starting to come through.
Oh, good. Okay, I'm glad that's the case.
We're just waiting for the graphic to. You're just waiting for the actual graphic. It said that you started screen sharing, so it should appear in a couple of seconds.
Yeah.
David, what I would suggest is maybe you can just unshare it and reshare it.
Okay, let me try
there
that.
we go. There we go. It's come through.
Has it come through?
Yes.
Great. Okay, I'm just going to, because I've got two screens here and I'd like to move one of them. Yeah, I'll move this one over here. And sure why that's there, but. So are you seeing my PowerPoint?
Yeah, it's actually stopped. So David, just stop it and reshare it again.
Okay. Sorry about this.
Not a problem.
Coming back.
Okay, you're seeing something.
There we go. Thank you, David.
Good. Sorry about that. Yeah, so maybe I should just go back to the previous slide. Strange, I don't have control of my PowerPoint slide for some reason. Are you seeing my title slide?
That's it. Things that go up in the night.
Good. Okay. Sorry about that. So let's see. Okay. So here's what I was talking about. The graphic on the left of two neutron stars which merged, causing this event that's now famous in astronomy. It's known by its name GW 170817. GW for gravitational wave, 17 for the year 2017, and 0817 because it happened on the 17th of August. And this is really when, I guess, our investigation into such transient events of merging neutron stars really began with this event. And we've attempted to continue to look for other examples of these merging neutron stars during the run that was followed up that just finished earlier this year. It actually was, it was called the O3 run of the LIGO Virgo gravitational wave observatories, which came to an end a little bit prematurely because of COVID-19. It was planning to be closed, I think, sometime in May, but it stopped earlier than that. But anyway, this is just an example of a very highly energetic event on the left. And on the right is an example of a more mundane, if you like, a comet, which are not, you know, not things which we are particularly concerned with. Of course, it's nice to see them, and there's a lot of good astronomy that's done on the study of comets, but it's not something that I'm involved in intimately. Although this image here was actually the discovery of one of the optical transient detection telescopes at Sutherland called is, as I say, something which has been increasingly active. It's in some cases and then cause a massive explosion has been the subject of a number of dedicated telescopes to look for supernovae, mainly because supernovae are indicators of distance and can be used in cosmological studies. And in fact, it was studying supernovae that led to our discovery that the universe is not only expanding, but the expansion is accelerating. So there were a number of different dedicated facilities, and still are. For example, there's the Assassin network of small, essentially camera lenses, I would say, rather than telescopes. They're something like 200 millimeter to 300 millimeter diameter telephoto lenses with CCD cameras mounted on common mounts, surveying the whole of the northern and southern sky to look for supernovae. Other types of, other transients are discovered as a byproduct of the main sun. Because it is doing this continuous mapping, discovers transient events, new stars where there weren't stars before, or highly variable objects where that wasn't known before. OGLE is another mission, which is a Polish-led optical ground-based telescope, which is also looking for optical transients. Sorry, I think there's some interference. Yeah.
Yeah, I've just muted the other parties. Sorry about that.
That's all right. And more recently, something called ZTF, or the Zwicky Transient Factory, which is the repurposed 60-inch Palomar telescope, has been doing a wide survey of the northern sky to look for transient events. And so there are both ground-based and space-based. Now has developed its own ground-based transient detection facilities. The one in the center there, Master SAO, began operating in 2015. I'll talk a bit more about that because I'm involved in that project. And the one on the left is Meerlicht, which is a smaller sized telescope, which is something, yeah, it's a telescope which is dedicated to look at the same parts of the sky that the Meerkat radio telescope is observing. So it's a 0.65 meter telescope with a wide field of view, several degree field of view, which matches the Meerkat radio array field of view. And it's looking for optical counterparts.
I'm losing your sound. I don't know if it's just me.
Yeah, I think it's probably on David's side. So let's just give him a second. David, I don't know if you can hear us, but your sound's cut out from our side.
It appears to be muted.
I am muted. You're right.
There you go, David.
Okay, can you hear me now?
Yes, we can.
Okay, I don't know why it went muted. I didn't mute it, but anyway.
Yeah, interesting.
So in 2016, we began this large science program with SALT to follow up on observations of transients. And it's paving the way for the next major sort of facility that will come online about 2023, which was known as the LSST, or the Large Synoptic Survey Telescope, an 8.3 meter telescope currently under construction in Chile. It was renamed last year to the Rubin Observatory in recognition of Vera Rubin, who was an American astronomer who has had this facility now named after her. And the LSST aspect of it has been kept, but instead of standing for Large Synoptic Survey Telescope, it now stands for the 10-year survey that this telescope will conduct, which is called a Legacy Survey of Space and Time. I guess they had too much paperwork with LSST written on it that they didn't want to go and change everything. Anyway, LSST, as you'll hear later in my talk, is the next big thing in transient detection. And it's something that South African astronomers are now becoming involved in as well, as I'll mention. And so the sort of lessons that we learn currently in doing the sort of transient follow-up on these smaller scale facilities will be a big learning mission for learning how to develop the machine learning tools that we will need in the era of the LSST, or the Rubin Observatory LSST. Because instead of dealing with thousands of transients a night, for example, from the Zwicky Transient Factory, it is finding of order of thousands of, or even tens of thousands of transients a night. LSST will be finding millions of transients a night. So there's no way that you can apply the sort of techniques that we do now, which is just essentially manually following up on transient observations. We have to have clever techniques, artificial intelligence and machine learning to do this. So I was mentioning the master facility, which is the local transient detection facility at Sutherland that began in December 2014. And it's part of a node of about 7 telescopes in operation now across the globe. Only 2 in the Southern Hemisphere, the one in South Africa and one in Argentina. And this is a Russian-led network by the Sternberg Astronomical Institute in Moscow. And it's basically surveying the whole of the sky to look for transients that are, say, brighter than about 18th magnitude or so. Although, in fact, the Sutherland site is so good that it's been able to detect much fainter transients as well. So here's a picture of master at Sutherland. It's actually 2 40-centimeter telescopes mounted on the same mount. It's a rather unusual design. It has a wide field of view, 2-degree field of view, and it has both a mirror and a corrector, and the actual detector, the camera, sits at the prime focus at that position number 5 in that schematic. And the reason why they have 2 is with a single telescope you get a 4 square degree field of view, but with the 2 telescopes you can offset them slightly with respect to each other to get an 8 square degree field of view. And that's what's used mostly when it's used in the mode for detecting transients. Furthermore, they don't use a filter, so they just use it in the standard white light of the CCD to look for and detect transients. But what they can do is when they do detect a transient and they want to do more intensive follow-up, then they can bring the 2 telescopes that have been misaligned back into parallel, and so they cover the same part of the sky, and they can put either 2 different filters or 2 different polarizers in the beam so that they can measure 2 colors at once or 2 states of polarization. The latter is quite a unique aspect, and it's been very important for the study of polarized transients, for example, gamma ray bursts. So the SALT Transient program, which is the follow-up program that is currently operating, it will continue to operate at least until the end of 2021, and we hope it'll be extended in light of the large productivity of this program in terms of discoveries and publications. The Transient program covers many different object classes. Basically, everything that I've written down there, the many object classes, everything from X-ray transients to novae, things called tidal disruption events, which are where a massive black hole tears apart stars that come too close to it. All manner of different types of transients have been the subject of this program. And since 2015, also the study of gravitational wave counterparts and looking for their optical counterparts, and even neutrino events, which are these events that are discovered by the likes of IceCube, which is a neutrino detector in Antarctica, or Antares, which is a similar observatory up in the Mediterranean Ocean, soon to be joined by something called K3MNet, which is a network of neutrino detectors. And then since last year, when Meerkat began its transient program, which is called Thundercat, we have also been looking at radio transients and doing optical studies of those. So the idea is that we're looking over a wide range of timescales for how these transients evolve, and we're moving into this sort of regime which is in the top figure there with the big question mark, which is things that vary on timescales of less than a day, even down to timescales of seconds. And so with the facilities that we have with SALT, and also with some of the smaller telescopes at Sutherland, we're able to do the follow-up of transients, pushing this time domain boundary to ever decreasing timescales, and also covering a wide range in luminosity or energy of these transients. And the little figure underneath that plot is just showing a result from this of that merging neutron star system, where the black curve is the spectrum that we got with SALT, and the various other curved, colored curves are various poorly fit models, except in the blue part of the spectrum. So the program, as I said, started in 2016. It's grown over the intervening period. It now has 5 South African institutions involved, including astronomers like myself at the South African Astronomical Observatory. It also involves some of our SALT partners in Poland, India, the UK, and the University of Wisconsin. And at last count, it has something like 36 co-investigators, including quite a number of graduate students as well. And in recent times, we have become also collaborating with astronomers in China and Russia, which is coming out of the BRICS astronomy working group, which I'll talk about more later. And as I say, there's a potential for it to expand into the rest of Africa as well as astronomy develops there. So you've probably all seen this picture before of SALT. I always like to show it. It's I think a very nice picture that shows conditions on a really nice day at Sutherland. And there's the heart of the telescope, which are the 91 1 meter edge to edge or 1.2 meter corner to corner mirrors, which shows you the huge light collecting area that we have with this telescope. And that means that we can look at things that are very faint, but also we can look at how things change very fast because of this large collecting area. And as you probably also are aware, SALT is a rather unusual design in that it cannot point to any specific place in the sky except within that annulus, which is shown in this figure. And only within those two blue lines, when a target moves across as the Earth rotates, are we able to observe objects. So that's a restriction that the telescope has. It's part of the compromise in keeping the cost of the telescope down to a fifth of what it would have been otherwise if it had been a general purpose telescope that could point anywhere. So all we have to do when we do this follow-up work is make sure that we know when an object of interest is inside that annulus. And for many events, it's perfectly adequate to be able to schedule observations, say within 24 hours of an alert. And so for most of the types of observations that we do, the fact that we cannot point it to any random place in the sky at night, we have to wait, is generally not that consequential, except for certain types of objects, which I'll talk about, namely gamma ray bursters. The nice thing about SALT is it's a purely Q-scheduled service observing operation. So there are astronomers that undertake the observations on behalf of all of the partnership. So the astronomers don't have to go up to use the telescope. They get the observations done for them. The data is available typically the afternoon following the night where the data was taken. Furthermore, we're able to dynamically and actively change the queue to add targets or update requests for, say, how often we want to observe a particular transient event. And we have the full variety of instruments available to us at a moment's notice. Changing between the instruments is trivial and quick. So to do targets of opportunity like transients are, is actually quite easy to do with SALT, which is why we have benefited, I think, in terms of being able to react much more quickly than many other telescopes can for this type of science. And so we have at our disposal 4 different instruments. The main instrument is the spectrograph at the prime focus of the telescope, the Robert Stobie spectrograph. We have another up there as well called Salticam, which is a imaging camera, and then a high resolution spectrograph, HRS. It shouldn't have Salticam in front of it, actually, that's a typo. And that's a fiber-fed high resolution spectrograph for brighter objects. And then there's also a photon counting image tube camera for very fast timing of, say, pulsars, for example. So all of these instruments are available to us at any time, given what the requirements are, what type of objects. So in terms of what we've actually observed since we began the project, this is a breakdown of the different classes of objects, and I'm going to give some examples of different ones in my talk. And a large fraction of them are, as you'll see, X-ray transients, the second most populous. And I'll talk about those in more detail because they're the sort of objects that I am particularly interested in myself. The other class at the top, which are Gaia, Ogle, Assassin, etc., are transients from these other facilities that I've already mentioned, which are typically things like nuclear transients in the center of galaxies, supernovae, microlensing events, and so on. Many of the observations that we do, we also harness other multi-wavelength facilities to support, sometimes even simultaneously, to get observations at other wavelengths. And in fact, with Meerkat, the new radio array here in South Africa, we've started to do that, and I'll show some results of the first observations that we've done that have combined SALT and Meerkat. Many of the high energy transients are discovered by virtue of X-ray or gamma ray emission, and that's only detectable by satellites, things like the Swift Observatory or the Fermi Observatory or the MAXI experiment, which is an X-ray telescope on the International Space Station, and NISA, which is another X-ray experiment on the International Space Station. So all of these high energy facilities also find transients, and then we look for the optical counterparts and study them from the ground with SALT and the other telescopes. Here's a recent example of an event that happened in December last year. It's a gamma ray burst, which is the collapse of a massive star, which causes a huge explosion and the ejection of a collimated jet of high velocity material. This artist's impression shows the jet coming out from the collapsing object, which would go in both directions. The jet would go towards us and away from us. And if you happen to be on axis and see the jet coming towards you, then you see this huge burst of gamma rays, which is how these things are detected. And this particular event that happened on the 21st of December last year, detected by these gamma ray satellites in orbit, was a particularly bright one, reaching 10th magnitude. And we were fortunate that because it was so bright, by the time when it was discovered, we had the ability to observe it with both SALT and a telescope in Chile called the VLT, the Very Large Telescope, which is a 4 8-meter telescopes. And furthermore, it was detected in the optical by the Master Telescope in Sutherland. And the light curve on the right there shows the declining brightness of the gamma ray burst. And if you look at the top axis, it shows you how quickly that Master got onto this gamma ray burst after the initial alert from the satellite. And you can see within 20 seconds, this telescope had slewed to the target and got its first data point, which is that first data point you see at the top left. And then you see that it declined, and this is in magnitude, so it's a power law plot. And so the flux declined from 10th magnitude to about 14th magnitude in only a matter of 1,000 seconds. And so when we got onto it with SALT was several hours later, but it was still at 16th magnitude, which is still very bright. Typically, GRBs fade away to fainter than 20th magnitude after this time. So we were fortunate that it was still at 16th magnitude, quite bright, and we got unique spectropolarimetry, only the second GRB to have spectropolarimetry and far better quality than any other previous observations. So this just shows you when things work out and you're lucky that you're able to detect it in time and it's bright enough that by the time SALT could observe it, that we were able to get this nice data. And the plot on the left there is just a spectrum of the object. It's a distant object at a redshift of over 1. Currently I'm working on a paper to write up these results, combining both the SALT and the VLT observations. I should also say that because we were onto this so quickly, we asked for director's discretionary time for a meerkat observation of this source, but only about a month after these initial observations, because the radio emission tends to lag. And so we didn't need to get instantaneous observations in the radio, and we actually observed it a month after, and it was detected. So this little image here shows the detection at a reasonable level of about 70 microjanskis, which just to give you an idea, 10 or 15 is a sort of limit. So this was a clear detection of this gamma ray burst. So that's an example of some recent exciting science that's come out of the Transient program just this year. And then earlier this year also, a paper was published from observations that were done last year of this bright nova in Carina, known as V906 Carina. And if you see here in this image, you can see, I hope, the flashing of the nova before outburst. Well, actually, it wasn't before outburst. It was during the outburst and up to maximum brightness. And the fascinating thing about this nova, which is really telling us a lot of new information about novae, is that it was observed simultaneously with an optical nanosatellite called Bright. There's a constellation of, I think, 3 small nanosatellites with small telescopes and cameras, which are looking at very bright stars to look at their pulsations. And this constellation of satellites was able to monitor continuously, without any interruption, the optical brightness of this nova. And that red curve at the top shows a sort of over 40-day continuous measurements of the brightness in the optical. And you can see it's not like a normal nova that we're used to, where it just gradually brightens and then begins declining. It shows these sort of bursts of brightness. And during the last part of the monitoring, it was observed by a gamma ray satellite called Fermi. And what they discovered was a correlation between gamma ray emission and the optical emission. And this was recently published in Nature Astronomy by a former student at SAO and UCT, Elias Adi, who's now a postdoc in the US, who had been leading the NOVA work on the SALT Transient program as a student, looking at other novae. And so this was a really nice example of both a fascinating object, but also showing how someone has developed in their career now to become a leading authority on novae. I mentioned earlier that some other types of events that are detected now include tidal disruption events. This little picture here shows what we think is going on in a tidal disruption event. It's when a star wanders too close to a supermassive black hole. You've probably seen and are aware that our own Milky Way has stars which are moving around an unseen black hole nucleus of our Milky Way. And we've actually tracked the orbits of about a dozen stars around that nucleus, and even seen flaring events where it's thought that a star might have been completely disrupted in such a TDE event. They've only really come to light in terms of optical observations in the last few years, although it had been predicted some time ago. And they evolve slowly. These are not sudden flashes. They typically brighten over a period of a month or so. And for this particular event, which was requested by our Polish colleagues in the collaboration, was bright enough that, again, we could do polarimetric observations, which was the first time a TDE had measured polarization, which tells you a lot about the sort of dynamics of how the material is torn apart by the black hole. So I'm going to now talk about some of the X-ray transients, and this is an area that I have more personal interest in. And X-ray transients come from binary systems where you have a compact central object, like, say, a black hole or a neutron star, or even a white dwarf, a compact star, the mass of the sun, but the size of the Earth. And these are in fairly close proximity to a more normal type of star, what we might call a main sequence star, like our sun, or maybe a bit less massive than the sun, typically for the so-called low mass systems. And they're so close, in fact, that we have what's called mass transfer, where mass is lost from the donor or companion star and typically forms a hot accretion disk surrounding the compact object. And that material in the accretion disk sort of goes, spirals around like water down a plug hole, and eventually accretes onto the surface of the compact object, if it was a neutron star or a white dwarf. Of course, with a black hole, there is no surface, so it passes through what's called the event horizon, where all information is lost after that. So we've been looking at all variety of X-ray binaries, and what's apparent is that these are not just quiescent, steady emitters of X-rays. They go through transient events where suddenly the amount of energy generated can go up by hundreds or thousands or more times the luminosity that they are when they're in their sort of steady quiescent state. And so some of the ones we've looked at are so-called high mass X-ray binaries, which are typically the companions are giants or even supergiants in very wide orbits with orbital periods of maybe weeks to months typically. And the other class of low mass X-ray binaries are much shorter orbital period systems, maybe days to even hours. And then there's a funny sort of subset of the latter, which are called millisecond pulsars, which are only a handful of them known. But these are systems where the central accreting source is a pulsar, a rapidly spinning neutron star, but its magnetic field is strong enough that for much of the time, accretion can't happen because the magnetic field basically sweeps the material out and doesn't allow it to get anywhere close to the neutron star. And in those sort of what we call ejector states, these things are seen as radio sources, as millisecond pulsars. But occasionally the mass transfer increases and the material penetrates the magnetic field and reaches down into the neutron star, and you get an increase in X-ray luminosity. And that's why they're called transitional, because they transition between accretion and ejection. So with the SALT program, we've been observing all these different types of objects. There's over 16 different systems that we've observed, with about 9 publications and many others in preparation, many of them involving and widening the experience of young South African researchers as well. So, for example, we've looked at high mass X-ray binaries, which are the ones with long periods and typically have a giant hot O or B type companions. And in these systems, the neutron star follows this sort of elliptical orbit around its companion. And when it gets close, there can be an episode of increased emission, which causes an outburst. And so we've been monitoring these types of systems with SALT. And as I say, this is one of the sort of things that have been quite productive. In the case of the lower mass black hole X-ray binaries, this is an example of a system that we've observed since 2016, where we did photometry, looking at the brightness of this thing. And you can see here 4 light curves from April the 28th, 2017 to July the 19th. And what you see is sort of little dips in the brightness But the most interesting thing is that the frequency of those dips gets longer. In other words, the time between the dips gets longer. So you can see in the first light curve, it's maybe only a couple of 100 seconds between the dips, whereas in the latter light curve, it's more like 500 seconds between the dips. And the explanation that's been put forward in now 2 papers that we've published on these results is that there is this thick torus of material in the accretion disk, which is has a sort of thickened extent. It sort of thickens up in the inner part, and those sort of vertical perturbations in the inner part of the disk rotate around with a typical period of about a few 100 seconds. And as these perturbations spread out in the disk, the period of rotation decreases, which causes the dip period to get longer and longer over time. So this was a nice example of looking at a black hole system which has these unusual optical activity. You don't see very much of the X-rays because you're almost looking at this thing edge on, and therefore the X-rays are absorbed by the disk of material surrounding it. But then further observations that we did in almost a unique mode that we have on SALT to be able to do fast spectroscopy showed that the spectral lines show dips as well. You can see in the bottom figure here, this is a spectral plot where spectra are taken every 30 seconds. And you can see that occasionally you see these black dots, which are basically absorption lines that come and go in, this is the H alpha line of hydrogen, but you see them also in helium lines and the other hydrogen lines. And this is exactly attuned to the idea that there is a hot, dense wind, a wind coming off the disk, which is causing these, and where it's thicker and comes into the line of sight, it causes this absorption. And the second paper on this that published these results was actually written by the former director of, or a former director of SAO, Phil Charles, who some of you may remember. So those are examples that were over the last year or so. This is an example just from this year, which was just, I guess, the paper has been submitted and a press release released on this. You might have seen it on the SAO webpage, where another system, which this time is not a black hole, but a neutron star, we have witnessed the turn off of enhanced mass accretion. And first of all, in the optical, where the optical light begins to increase over here, and then a delay of many days before the ultraviolet emission begins, and then the X-ray emission begins. And this is all explained by material that's gradually coming into, through the disk, moving in slowly towards the center. And as the disk has more material being added to it, it gets brighter in the optical, which is why it begins to rise in the optical emission. But it's not until that material hits the white dwarf, sorry, the neutron star, or close to its magnetic field, that we start to see the high energy photons from the ultraviolet and the X-rays. So the sort of picture we have of something that looks like this with a spinning neutron star should say that neutron star is spinning about 400 times a second. So it's a rapid spinning pulsar. And because it's magnetic, the material threads down onto the magnetic fields. And so this is another example of an exotic object where we've been able to get some really nice observations. I'm not going to go into details of this one, but this is an example of another similar X-ray source, but involving the accretion of a white on a white dwarf. And this is a schematic of what we think it looks like. Again, it was something which was published about a year ago in Nature Astronomy, and it's known as a super soft source. It means it's an X-ray source, but it's a very low energy X-ray source, or what we call soft X-ray source. And the explanation for why it suddenly started increasing in its brightness was because of a very hot development of the inner part of the accretion disk and what we call the boundary layer, or the spreading layer of the accretion disk as it interacts with the white dwarf. Other types of accreting white dwarfs that we've observed with in this program have include magnetic cataclysmic variables, which is something that I did research on when I first came to South Africa in, I guess, the late 80s. So these are systems where you have a white dwarf in something like a few-hour orbit with, say, a low mass lower mass M or K type main sequence star. The difference between these and normal cataclysmic variables, which are just non-magnetic white dwarfs, is that the magnetic field is strong enough to grab the material and thread it onto the magnetic field lines, which then follow down onto the magnetic poles of the white dwarf. And this leads to X-ray emission, which is how often they're discovered, but also significant polarized emission. So they're often seen as strongly polarized objects. And this particular observation that I'm showing here is of a system known as UZ4, which was observed in 2018, where we did simultaneous meerkat and optical, both SALT and the SAO 1.9 meter, and the Meerlicht telescope observations. And this was work that was carried out by a PhD student, Zwida Kangali, who's finishing writing up his thesis right now as we speak. And so we got the very first simultaneous meerkat and ground-based optical observations ever of anything, which happened to be this particular object. And we got a nice light curve with the 1.9 meter. You can see it's an eclipsing system. But furthermore, we got really nice spectropolarimetry. As I say, these things, these magnetic CVs are often strongly polarized. And in this case, we detected the strong circular polarization across the spectrum of this object. Almost, again, a fairly unique capability that SALT has. So I'm going to finish up with some discussions about future transient work, and some of the work has already begun with the local facility called Meerlicht, this 0.65 meter telescope, which began operations last year. It's a joint Dutch-UK SAO venture, and the idea, as I mentioned earlier, is that this telescope is basically slaved to follow meerkat. Whenever meerkat is observing, then obviously at night, we can't do observations in the daytime with Meerlicht, that we will follow to see that if any radio transient happens to be detected by meerkat, we will have the simultaneous optical observations. And so this is a unique facility. There's no other telescopes I'm aware of in the world that has this unique combination of optical and radio. And so this is something which is just really starting to do its science now. And then other telescopes which are also involved in transient follow-up include the newly operating telescope called the SADI, which is a 1 meter telescope, which at the moment is still being commissioned, but we are getting observations with it. That's the telescope on the right. And also Monet South, which is a 1.2 meter telescope run by German University of Göttingen. So these smaller scale telescopes are being used in conjunction with SALT to follow up on certain types of transient objects like cataclysmic variables and blazars and so on. And, other facilities that we have at Sutherland include KMTNet, which is a Korean telescope, a 1.6 meter wide field telescope. There are 3 of them around the world, one in South Africa, one in Australia, and one in Chile. And beginning this year, we're starting a program to image a large fraction of the southern sky in preparation for example, finding counterparts to gravitational wave events and preparing for what I mentioned before, the next big thing in transient detection, which is the Rubin Observatory LSST. And then another telescope which will hopefully begin operations next year. We are hoping to finish the construction of the building by January and the installation of the telescope next year, is a wide field 1.8 meter telescope, but working in the infrared. And this is mainly to look for microlensing events for detecting exoplanets in the infrared, but it also has a strong science driver of observing transients, doing follow-up of transients. And so this telescope will be an important cog in the wheel of transient follow-up. And that brings me to this slide, which is our future aspiration in the development of something called the African Intelligent Observatory. And what this is a project to basically automate and network all of the, or many of the telescope facilities we have on the Sutherland Plateau to do follow-up of transients, not just the detection of them, but to do the follow-up of them. And so this can potentially involve about 11 telescopes on the Sutherland Plateau in various roles in terms of following up. And so what it involves is this schematic here where I've shown, for example, alerts coming in from externally. So, for example, the SWIFT gamma ray detection satellite, the very same satellite that detected that gamma ray burst I mentioned earlier. That's a source of an event. We have our local alert facilities like Master and Meerlicht at the top right. So these events will be basically assimilated automatically and then send instructions to other telescopes on the plateau to do the follow-up observations, be it SALT or the other telescopes, some of the other telescopes that I've already mentioned. And this is work which is being done here in South Africa, but it's parallel to what is happening globally to really take the manual operation of telescopes away from astronomers and to turn it into an automated follow-up machine, which has its own intelligence to make the decision-making of what sort of objects are worth following up and then what type of observations can be done. So there's been a huge amount of investment in developing what are called event brokers, which are software systems that take in the information about a particular transient, then decide probably what it is on the basis of the information that might be known, and then determine what type of appropriate observations should be conducted to probe further and find out more about what the object is. And this all leads into this new project that I mentioned before. I should have updated this slide because it's not called the Large Synoptic Survey Telescope anymore. It's called the Rubin Observatory Legacy Survey of Space and Time. But this is going to do a 10-year survey of the whole of the southern sky with this 8.4 meter telescope. You can see it there before it was dismantled and shipped to Chile. It was built in Spain. It will do observations of the whole sky in 5 filters every few days. And it will reach magnitudes of something like 25 to 26th magnitude. So this is a deep, wide survey of the entire sky that's going to detect, of course, many variable and many transient objects. And it includes international participation, and more recently, since last year, South African participation through the funding of what's called principal investigator affiliates. So there are 3 of us who have been appointed as PIs on the South African program, and I am running a group which is interested in transients, and it involves other people like Patrick Vogt, Professor Vogt at the UCT, Steve Potter at the South African Astronomical Observatory, and others, and students as well. And so we are getting ready to prepare for this, this new groundbreaking telescope when it becomes operational in about, well, it will start commissioning in 2022 and should become fully operational in 2023. And finally, I'm just going to mention another initiative which is being driven through the BRICS consortium. So you might be interested to know that there is something called the BRICS Astronomy Working Group. It's been running since, I think, 2017. And in particular, it has converged on a proposal to develop a flagship program on transient astronomy. It's called the BRICS Intelligent Telescope and Data Network. And it was adopted at the last meeting in Rio last year in October to be the main project to be pushed forward and to be supported by all 5 BRICS countries. And the long-term goal of this is to develop a network of the order of 70 1-meter telescopes, each with a 25 square degree field of view in both hemispheres, that would cover the whole sky simultaneously and take observations roughly every hour. So only being 1-meter telescopes, it will get down to about 20th magnitude, so not as deep as the Rubin Observatory LSST, but with a time variability, a cadence of an hour compared to several days. So it opens up again the potential for a whole new discovery space of very fast varying transients. And the hope is that this will be supported by the BRICS consortium. The Chinese are already developing, and the Russians are already developing designs for these telescopes, which is making use of new wide field optical designs coupled with SCMOS detectors, fast scientific CMOS detectors. So this may be a future program where the BRICS consortium would be leading the world in high cadence transient detection. And that brings me at last to the end of my talk. I'm sorry I went over my what I thought would be my 40-minute time scale. So, yeah.
Thank you so much, David. We don't mind you going over time. That was wonderful. Thank you so much. We really enjoyed it. And I think, we're a bunch of people that like to get involved with the nuts and bolts, and we really enjoy a technical talk, and this was really awesome. I'm just going to do the necessary technical changes here.
Yeah, I'll stop sharing.
Thank you.
Dr. Buckley, is HET still operating?
Yes, it is actually. So HET had a major refurbishment about 3 years ago. So they changed the so-called corrector to give it a much wider field. I don't know if you know the details about HET, but it was the precursor of SALT. And when SALT was designed, we changed the design so that we had 4 times bigger field of view than the HET. Now the HET have leapfrogged us to have a larger field of view still. And it has one major science driver, which is looking at Lyman break galaxies. So it's a cosmology machine, which is doing a very, focused on a very specific task. But yes, it is fully operational.
Thank you.
Right, thank you so much. So, guys, now is normally the time where we allow our audience to participate in question and answers. So you're more than welcome to raise your hand via the raise hand function in Zoom, or you can just put up your hand. You can activate your video and put up your hand. So is there anyone that's got any questions for David? Frank, you can unmute yourself and you can pose your question.
This is Ian. You didn't then say anything about the Las Cumbres Observatory, as far as I remember.
Yeah, I didn't. So as you know, Las Cumbres is not part of the SAO group of telescopes, in the sense that, like the other telescopes on the plateau, well, many of them are SAO facilities, but we make use of LCO. So, for example, there are a couple of programs that we have for follow-up of cataclysmic variables and blazars, which are run on the LCO system. And in fact, LCO are also developing the software which allows for the what we call a marshal, a system where events are selected and then scheduled for observation. So LCO have a lot of experience in this because it's purely robotic telescopes. And so we have in the process of adopting similar sort of protocols, software protocols for these event follow-ups with LCO.
Thanks.
Right, I see that Frank, you've got your hand up. Do you still want to ask a question? All right, I can open up the floor to anyone else. You guys are, by the way, more than welcome to switch your video back on and unmute yourself.
So can Marius, if I could just make a comment.
Sure.
Yeah, David, what a enthralling presentation. You, I find it absolutely fascinating, and I was hooked on every bit of data you displayed and spoke about. Well done. I really think this is one of the most one of the best presentations I've listened to and had the pleasure of learning from. Thank you very much.
Well, thank you, Martin, for those comments. Yeah, I mean, the world of transient astronomy is huge, and I haven't done it justice in many respects, because there's some things I just didn't have time to discuss. Something that might amuse some of you is because I'm sort of, I sort of see myself as an orchestra conductor with my team of, collaborators. And of course, an orchestra is only as good as its instruments and its individual musicians. So there's a lot of people who have put a lot of effort and continuing. So this is not one person. This is many people. At the moment, the way things happen is that I'm a sort of a conduit for requests to add targets, for example, and I do this typically in the later part of the afternoon, because often that's when alerts start coming in. And the word transient in my family with my wife and daughter has become a bit of a bad word, because invariably at dinner time, when I'm told dinner's ready, I reply, hang on, I'm just submitting a new transient. And so, yes, it's...
I can understand that. Well, I just, again, thank you so much. It really was from start to end was you captured my attention 100%, which is quite something, because I'm one of those skittish brains that just bounce all over the place, and attention span is slightly less than the average goldfish. So, I really, it's one of the best presentations I've seen in many, many years. Thank you.
Thank you.
So in your house is dinner transient?
What was that?
In your house is dinner transient?
Ah, right. Yeah. Well, sometimes dinner has to wait, which is what annoys my wife and daughter.
Guys, I see that Kevin has also got a question. Kevin, you're welcome to unmute yourself and pose your question to David.
Hi, thank you, Professor, for an amazingly informative talk. I'm quite overwhelmed with all the data that was being thrust into my grey matter, but no, amazing. I'm just curious, though. In one of your earlier slides, you had a comparison of the, I think it was the magnitude of the transients, general transients that are captured, or it was the flux. But my question is, and it might, what is the faintest transient that has been captured globally, as far as you're aware, and then by SAO instruments?
Right, you mean in like optical magnitudes?
Yeah, well, basically would have to be, basically optical magnitude, because you mentioned 25 mag. I would have thought that, granted the observation periods are very small, but surely the longer the observation periods, the deeper you go.
Yeah, it's not quite like that, because the problem is you have a background emission from the sky, and so you have in a sense a sort of additional noise on your signal, and for the fainter the objects, the more that background signal contributes, and removing that background signal is a big challenge. And so that's what sort of limits us with SALT. I think the faintest object, which was an X-ray source on the other side of our galaxy that we observed, was around about 25th magnitude in the R band, in the red. So that's probably the faintest that I'm aware of. But I should make the point also that SALT is not ideally placed for doing imaging, just taking pictures of stars. It's better at doing spectroscopy, where you split the light into its component colors. There are other telescopes in the world at better sites, like in Chile, which have much better capability for imaging, which gets them to even fainter. And also many of those telescopes employ techniques like adaptive optics, which removes the effect of atmospheric blurring. And so that's, that's why, we can't sort of push it down much beyond that with salt.
Well, thank you very much. But I think that's the amazing thing. I think different countries, obviously because finance, it comes to the bottom line of many things that, I think there's a place for everywhere. And salt really is, and meerkat really is amazing. Just to think of a South African or African context, what's been achieved, is beyond, I think, anyone's imagination in the last 20 years. Thank you.
I completely agree. I mean, we had a conference here in February called Transients 2020. It was a meeting that was sponsored by the International Astronomical Union and the Kavli Institute, and it had key players globally. It was by invitation only. It was a very small meeting, and it had a particular goal to come up with some recommendations about how various things should be done. But one of the people who was from Caltech made a comment in her talk, and she's one of the people running the Zwicky Transient Factory and the follow-up of that, that SALT was beating the pants off other 8-meter class telescopes, like, for example, Gemini. The reason being is that we are so flexible that we can react much quicker to some request or some alert, whereas these other telescopes typically are not scheduled in this sort of queue-scheduled mode, or there's just more latency between when a request is made and how they can follow up. But she just showed the statistics of the number of objects that SALT managed to follow up, particularly during the 03 campaign of Virgo LIGO, the gravitational wave observatory, compared to Gemini. And I was quite surprised to see that we were actually way ahead. And I think that sort of reflects the fact that although we're not in the best site in the world, we're not on top of Mauna Kea in Hawaii or in Chile, so the seeing's not so good. But in many other respects, we have distinct advantages. And I think we have found where we're competitive. And the SALT transient work is an example of our competitiveness.
Absolutely. Well, best of luck, and I'm sure me and many others, millions of others, will be watching all the latest GWBs that come out.
Yeah. Well, I mean, the other thing is that we're fortunate that we're back into operation. We did shut down for the lockdown for about 3 weeks, but we now have been in full operations remotely, I should add. So the SALT astronomer and the SALT operator are actually running the telescope from their homes, just on their laptops. And of course, there are technical people living at Sutherland who can, respond if there's a fault or an issue. But all our telescopes are being run like that. I mean, even last week I was remotely observing here in the SAO on the 1-meter telescope. And likewise, all the other telescopes are all being run remotely. Many of the telescopes in Chile are still closed. And so we're getting increasing requests from our international collaborators to observe things because they're not getting time either with Keck. Keck has just reopened actually in Hawaii, but certainly the Chilean telescopes are still closed.
Amazing. Thank you very much. That really was an amazing talk, and I've heard quite a few from ASA, but that's surely one of the top. It was a lot of information to digest, and must be a lot to manage.
Yeah, a lot to manage. Actually, I must say, I see someone here who you all know, Christian Hetlager. And I just want to have a shout out to Christian because he's the guy who's developed a lot of the software for proposal and target submission. And he probably, shudders to think whenever I email him because it's invariably, Christian, something's gone wrong with this. Can you help me with that? Actually, recently it has been running very, very smoothly, but I really like to recognize Christian's efforts because he really has done a lot for me and for our group in supporting our program.
Excellent.
Thank you so much. Christian, well done. Well, thank you, guys. I did see that Frank also had a question. Let me just quickly look at, yeah, Frank Delman, you're welcome to pose your question. I see Frank is unmuted and he's got his hand up, so we'll give him a minute or so. Right. Is there anyone else that's got any more questions for David?
Maurice, if I could ask a question, please.
Yes, Richard, you've got the floor.
Oh, okay, thanks very much for the talk, most informative. Tell me, the Rubin telescope, is it thought that it's going to be affected much by the Starlink constellation of satellites?
That's a really good question. And the answer is most definitely it is. And in fact, I was in a video conference last week with people involved in the transient and variable star collaboration of the Rubin Observatory. And one of the people who's a collaborator of mine reported back from a conference she'd just been to with the Starlink people and other satellite providers, where they were talking about the impact on astronomy and particularly the Rubin Observatory. And as you probably know, they're predicted that there will be something like 80,000 of these satellites in orbit. And for the Starlink ones, they managed to negotiate with Elon Musk to ensure that, well, to do at least firstly an experiment where they've painted one of these satellites black, just as an experiment to see what difference it makes in the brightness. And it makes about a 1 magnitude difference, changing it from 7th magnitude to 8th magnitude. And the issue, though, is that it's not so much the trails which will go through the field of view. It's the potential for something that bright saturating the CCD detector and therefore making a large part of the field totally useless for science. So there's that aspect. But the other aspect, which is, I think, more critical for one of the main science drivers which the Rubin Observatory has, and that is to detect all near-Earth objects, potentially hazardous objects that intersect the orbit of the Earth and could cause an event like a Tunguska type event or a Chebrolinska type event, you know, the one that was in Russia a couple of years ago. There is a mandate for the Rubin Observatory to discover all such objects down to, I've forgotten the size, but it's, I think, of the order of 20 meters or something like that, maybe more than that. It's a congressional mandate, actually, from the US Congress that the telescope has to meet. Anyway, the way that you find some of these is, well, the only way you find them is in the twilight period. And in particular, the ones that are coming from the inside of the solar system out towards us may never be observed because of the impact of these satellites. And so it is a worry and something which LSST is in negotiations with, for example, the Starlink satellites and Amazon. But there's also the worry of the large plans for the Chinese to also produce these microsatellites. And so, yeah, it really is a worry and something which I think the IAU will have to take on in terms of trying to see what they can do to mitigate this.
But is there anything legal? Is there anything legal that can be done?
Well, that's what I was saying. I mean, as you know, in the radio, there are certain bands which are free from broadcast, which are protected. Unfortunately, there isn't the equivalent in the optical. So, I think it will be a very difficult proposition to legislate against these. There's just too much vested interest and too much money potentially. But maybe some mitigation. I mean, even if the orbits of these were 100 kilometers higher, then the effective magnitude would be decreased significantly. And so, for example, I think the Amazon constellation of satellites are somewhat higher, planned to be in somewhat higher orbits. So they will be a bit fainter than, say, the Starlink ones.
Great. Okay, thanks a lot.
Thank you, Richard, for your question. Right, guys.
Can I just ask, has anyone seen these satellites, by the way?
Yeah, I spotted Starlink, from a house in Edgemead about 5:30 in the morning. It was quite a sight, I must say. I'm not very excited about it, but it's quite a sight.
Yes, yeah.
One thing that worries me, sorry, just to come back for the second, David, is whether it's legislated or not, and I deeply doubt that there will be a global legislation to stop satellites, because we know they are the future in terms of data communication worldwide, and Amazon is worth more alone than, you know, most governments in the world. But the problem is, you know, I'm sure you know, putting it up is not the problem. But if we decide it's now, you know, let's say in 10, 20 years, it's destroyed observational astronomy on Earth, how do you get them out again? Because they don't follow orbit. You can't just go out there and grab them. I mean, we all know about space junk. So that the bigger worry is each one that goes up is a massive problem to bring down. Anyway, you know, negative note, right. But reality.
You're dead right. It's a big worry.
Yeah. Okay. Thank you.
Thank you for the comment. Right, guys, I think that then brings us to the end of tonight's formal presentation by David. David, from Cape Centre, we'd just like to extend a very big thank you for taking the time out, and I'm sure that you are a very busy person, and for, you know, as said by quite a few people in the audience, for a wonderful presentation. You know, we all love, as I said, a good technical talk, and you covered everything, and it was brilliantly presented. Thank you very much.
Well, it's been a great pleasure, Marius, and everyone. I really enjoyed this, and in this difficult times that we're in, you know, this is the way we sort of communicate nowadays, unfortunately. Hopefully, at some point, I will see some of you in person again at a meeting of the Cape Centre. I mean, I see a number of people on the list like Matchy and John Richards, who I know from, you know, a long time. And yeah, I don't know when I'll see you all again, but in the flesh, that is, over a cup of coffee or something. But yeah, it was a great pleasure, and I was only too pleased to do it.
Thank you very much once again. Hi guys, thank you so much for taking the time out to join us. There's just one or two Cape Centre things that I just quickly want to discuss. As I said, you know, previously we got a new